A baseball leaves your hand moving forward. A moment later it is still moving forward, yet its speed is smaller. Gravity bends its flight, but gravity alone does not explain the lost horizontal speed. So what is pushing backward? Not a hidden tether and not motion running out. The ball is moving through air. That relative motion creates an aerodynamic force. Our question is simple. Why does air make a forward-moving baseball slow down? Air resistance is usually called drag. To know its direction, first measure the ball's velocity relative to the air. Subtract the air's velocity from the ball's velocity. In still air, relative velocity points forward, so drag points backward. In a tailwind, the relative arrow is shorter and drag is weaker. If the ball and nearby air move together, relative velocity is zero and so is drag. The rule is not opposite the ground velocity. It is opposite the velocity relative to the air. The ball can keep moving forward, while a backward force reduces its speed. Now fence the model. Taylor deliberately studies a spherical projectile that is not rotating. For an ideal smooth sphere, symmetry leaves no preferred sideways direction, so the aerodynamic force is drag alone, opposite the relative flow. Break that symmetry and the story can change. Spin a baseball, tilt a non-spherical body, or shape a wing, and the air can exert a component perpendicular to the relative velocity. We call that component lift. Lift need not point vertically, it means sideways relative to the flow. Airplanes require it. Our model sets lift to zero so we can isolate drag cleanly. That is a stated simplification, not a claim that lift never exists. Two properties of the medium will matter, and they are not synonyms. Density is mass per volume. Equal transparent volumes can contain different masses. The denser volume is heavier, even if it pours just as easily. Viscosity measures resistance to shear, how strongly neighboring layers resist sliding past one another. In the shear cell, the top plate tries to drag one layer past the next. A more viscous medium demands more force for the same velocity gradient. A fluid can be dense without being very viscous, or viscous without being especially dense. Density answers, how much mass is here? Viscosity answers, how strongly does the flow resist being sheared? At very low relative speed around a small sphere, the fluid rearranges smoothly. The sphere creates a velocity gradient. Fluid near its surface moves differently from fluid farther away, so viscosity transmits shear through the surrounding layers. Double the creeping speed and the shear rate roughly doubles. The viscous drag doubles too. That gives the linear term, F linear equals BV. Here B is an effective coefficient. It depends on the medium's viscosity and on the object's size and shape. In the special Stokes flow limit for a sphere, B equals 6 pi mu r. That formula has strict assumptions. The big idea is the linear scaling and its viscous origin. Now send the baseball through air fast enough that it must continually accelerate and redirect a substantial flow of air. Watch coherent stream tubes, not individual molecule impacts. In 1 second, the mass of air processed grows roughly like density times frontal area times speed. The amount each part of that flow changes momentum also grows with speed. One factor of speed comes from how much air passes, another comes from how much its velocity changes. Together they produce the quadratic scaling. We write F quadratic equals CV squared. A common form is C approximately 1/2 rho CdA, density, reference area, and a shape-dependent drag coefficient. This is inertial or momentum-flux drag. The two mechanisms can act at once. For ordinary subsonic motion, Taylor's useful model adds their magnitudes. F of v equals bv plus cv squared. The vector force points opposite the relative velocity unit vector. B and C are not universal constants. They summarize the chosen object, medium, and flow regime. B carries the effective viscous contribution. C carries density, frontal area, shape, and other flow dependence. At zero relative speed, drag is zero. This is a range-limited model, not a law for every possible speed. Before using the equation, read its graph. Speed lies along the horizontal axis, drag magnitude lies vertically. The linear term draws a straight line from the origin. Double speed, and that contribution doubles. The quadratic term begins flatter, but curves upward. Double speed, and that contribution becomes 4 times as large. The total curve is their vertical sum. At low speed, the straight line contribution lies above the parabola. At high speed, the parabola overtakes it. The graph shows why a baseball's drag can grow much more rapidly than its speed. It also turns a vague phrase, like low speed, into a question we can calculate. Where do the contributions cross? At the crossover, the two terms are equal. BV star equals CV star squared. For a non-zero speed, cancel one V star and get V star equals B over C. Divide the quadratic term by the linear term, and the ratio becomes V over V star. Below V star, that ratio is less than 1, so linear drag dominates the drag model. Above V star, it exceeds 1, so quadratic drag dominates. At the crossing, they are equal. Dominates means larger than the other drag term. It does not automatically mean drag is larger than gravity or every other force. Now use the classifier. A small sphere creeping through a viscous liquid can lie far below its crossover, so the linear term is the useful approximation. A baseball moving through air is large and fast enough that quadratic drag overwhelmingly dominates. In Taylor's rough sphere in air estimate, at 5 meters per second, the quadratic term is hundreds of times larger. But air alone does not choose the regime. A microscopic oil droplet moving very slowly through that same air can be linear drag dominated, while an intermediate raindrop may need both terms. Change the speed, the medium's viscosity or density, the object's size or its shape, and the crossover moves. Regime belongs to the whole object flow system, not to the medium by itself. As relative speed approaches the speed of sound, in the medium, compressibility matters. Density and pressure changes, and eventually shock structures, can change the drag coefficient, so fixed B and C become too simple. This warning concerns the speed of sound, not the speed of light. We use it for sound speed. The lowercase c in CV squared is only a drag coefficient. Nothing here is relativistic. The baseball slowed because its motion relative to the air created backward drag. We can now choose a linear, quadratic, or two-term model and defend the choice. Next, we place drag beside gravity in Newton's second law and watch the projectile path change.